So I suppose we were here in our previous lecture. We had come up till here. If you remember, we had worked out the details, and on the left hand side here we had an electrical network, and we had 4 bits. So the resistances were connected to the inverting end of the operational amplifier through these switches, and there was a particular combination of the resistances. These switches actually, they play the role of the digital representation of numbers. So this is the digital domain. Usually we put these switches on or off through the computer, in the sense we can send out a word or we can send out a byte. So here representatively we only got 4 bits, so it's just a nibble. But in actual practice you may have a byte, 8 bits or 12 bits or 16 bits, depending upon the ability of the digital to analog converter. And we are making use of an operational amplifier here. Then we saw in our last lecture that we could apply the principles of the operational amplifier and come out with the expression for the output voltage that would be produced based on the combination of bits. So it's essentially a conversion from the digital domain to the analog domain. And we could see that depending upon this pattern which is available here, the values, the specific values of B0, B1, B2, B3, we get specific values of the output voltage. This is in the analog domain. And here we are just putting on or off these switches. And if we proceed systematically, we can see that the smallest voltage that can be generated by the digital to analog converter is Vs, which is your voltage which you are applying, that is the maximum, divided by 2 raised to 4. 4 is because of the 4 bits that you have here. If we had 8 bits, we would have had Vs divided by 2 raised to 8. So that would have been the smallest voltage that can be generated. So now we will let us see the let us just try to understand. Here we have I've just reduced the size of the previous slide here and shown it over here. So we have these various bit combinations, B0, B1, B2, B3, and we are going from 0, 0, 0, 0, gradually incrementing bit by bit. Okay, we're going from here to here, and we start with 0, 0, 0, 0, and after incrementing we come finally to 1, 1, 1, 1. So in decimal terms, this corresponds to 0 and this corresponds to 15. So according to our calculations, we have got 16 steps, 2 raised to 4. So the smallest voltage that can be generated by this DAC is going to be Vs divided by 2 raised to 4. That means Vs divided by 16. Now, when you output the bit pattern 0, 0, 0, everything is 0. So the output of the DAC is 0. We also represent this digital domain using these boxes. It is just an icon. It doesn't mean that there are only 4 bits here. In general, it could be 4 bits, 8 bits, 12 bits, 16 bits, and so on. But this icon says that here you have the digital domain and here you have the analog domain. So it's a digital to analog converter. So this is the symbol we will use for the digital to analog converter. So depending upon the values that we have for B0 to B3, starting from 0, 0, 0, 0 to 1, 1, 1, 1, we go step by step. So suppose you are here, you have 0, 0, 1, 0. That means you have the bit pattern 0, 0, 1, 0 corresponding to 2 Vs divided by 2 raised to 4. That means Vs divided by 2 Vs divided by 16. That means Vs divided by 8. So if Vs is 10 volts, then Vs divided by 8, 10 volts divided by 8. Okay. So this is how you are able to go from 0 volts up to 15 divided by 16 multiplied by Vs. You can't achieve the entire Vs. Now, if you have more number of bits, you can approach closer and closer to Vs, but you never touch Vs as such. So this is the compromise which you have to make because of the digital domain. But it doesn't matter, because when you are dealing with circuits, when you are dealing with so small voltages in the real world, this does not make much of a difference. In fact, if you have higher resolutions, they are hardly distinguishable. For example, if you have say if you have 8 bits over here, so you can go up to 2 raised to the power 8 minus 1, 256 minus 1, 255 divided by 256. So that's almost equal to 1 multiplied by Vs. Okay, so you can approach Vs very closely. Another point which is worth mentioning here is the smallest voltage that can be generated by the digital to analog converter. You can see that it's very difficult for us to produce such a small voltage normally. But here, in this case, you can see just by putting on these switches, if you have 8 bits, then you can go, you can have the smallest step as Vs divided by 2 raised to 8, that is Vs divided by 256. And if you have 12 bits, you can go Vs divided by 2 raised to 12, that is Vs divided by 4096. And that is really small. So you can go up to millivolts, maybe even smaller. So that is how you can get very, very fine voltage steps using this digital to analog conversion. Naturally, if you want very good accuracy, you are going to have more number of bits for your digital to analog converters. But more number of bits means you are having a more expensive setup. These digital to analog converters are very inexpensive. Today they are very cheap. Maybe you can get them at 20 rupees, or 8-bit DACs or 12-bit DACs you can get for 50 rupees. They are very, very cheap. Okay. So of course you need to have the other components, the resistances, etc. Some other time maybe we will work out the economics of this, and you will see that it is actually very, very cheap, and you can even do it as a hobby in your home, and you can see it for yourself how the voltage is produced. Let us proceed further. Let us take an example. Now here um, we have, in this example, a digital to analog converter is required to generate a voltage in the range of 0 to 5 volts with a minimum resolution of 100 millivolts. Digital outputs, that is DOs, are used as inputs to the digital to analog converter. Design the DA converter circuit for the application with minimum number of bits using a resistive network. Prepare a sketch of the circuit design and label all components. Derive the expression for the voltage output of the above DAC based on the bit status and work out the resolution voltage of your design. Now, this is a very simple example, but it is meant to get you a feel of the digital to analog converter. Here you have the digital to analog converter, and you're going from 0 volts, from 0 volts here to 5 volts. Okay. And you want a minimum resolution of 100 millivolts. The range which you have is 5 volts. So let us say that let the number of bits required. So let the minimum number of bits when you do a problem, you should do it with steps. I may miss some steps here, but you will have to be careful. So let the minimum number of bits required be n. Okay. So we are assuming that we have a n bit. It could be 4, 8, or whatever, 4, 5, 6, 7, 8, whatever. Let the minimum number of bits required be n. And we have the range here. So let us see what is the number that is going to accommodate within this n. So we have let the number of steps needed to divide the range. So we are going to divide this range of 0 to 5 volts the range of 0 to 5 volts uh, with minimum resolution of 100 millivolts. So let this number be equal to C. Okay. Count, let's say, number of steps. Now, what should be count equal to ideally? So this range from 0 to 5, okay, we have this range from 0 to 5. So we are going to break this range into C different steps. So we require C will be equal to 5 volts is the upper limit minus 0 volts, which is the lower limit, divided by the smallest value, that is the minimum resolution, that is 100 millivolt, that corresponds to 0.1 volt. Okay. So this is going to be equal to 5 divided by 0.1, which is 50. I hope all of you agree to this. So we require 50 steps. Okay. Now, how are you going to represent, how many bits are needed to represent 50? So we have n bits. So you can see 2 raised to n should be either greater than or equal to 50. Okay. Or and 50 should be more than 2 raised to n minus 1. That means now in this particular case, because it's a very simple range, it's just 50 steps, it's easy for us to understand. We can take n as equal to 6. If we take n as equal to 5, we'll get 2 raised to 32. So 2 raised to 5, that is 32. So 32 will not serve the purpose. So we'll have to go to 2 raised to 2 raised to 6. If we do 2 raised to 6 greater than, or it is 2 raised to 6 is 64, and 50 is certainly less than 64, and 2 raised to 5 is 32. So this is 32. I hope all of you can hear me.
Yes, sir.
Okay, fine. So you can see that the minimum number of bits. Can you tell me what will be the minimum number of bits that will be required? If we choose, should we choose 5 bits or 6 bits?
6.
6. Because if we choose 6 bits, we can go up to 64. So we will have the minimum count, we'll have 50 steps possible. But if we choose 5, then we can go only up to 32. So with a 5-bit register, we will not be able to achieve our resolution of 100 millivolts. Okay, and so n should be equal to, so therefore n should be equal to, in this case it should be equal to 6. Now, of course, you could have used the logarithms method to do this as well. So you could have done 2 raised to n is equal to 50, and then you could have taken logarithms and done it. Okay. Now, this is a very simple example, and so, but if you have very large numbers, okay, instead of 50, you had much larger number, then you could have certainly used the log method and done it. So here we have seen now that the first part is over. We require 6 number of bits in our register, in our digital to analog converter. Okay, so minimum 6 bits. So DAC, the DAC should have a minimum of 6 bits.
Excuse me, sir.
Yes.
So I have a doubt here.
Yes, please.
So
Yeah.
since we have a minimum resolution of 100 millivolts, so sir, if we increase the resolution, the number of steps would decrease. Then
Yes,
we
you're right.
go for 2 raised to power n greater than equal to 50. Because if number of steps would decrease, then we should have the number of bits should be less than 6. Like the possibilities there, it can be less than 6.
Yes, but we are working it out for minimum resolution of 100 millivolts. That means we should be able to produce at least by the smallest step increment, we should be able to produce uh, a resolution which is less than 100 millivolts, not more. It is a minimum resolution. Okay.
Okay, sir.
If you, for example, if you use 2 raised to, so what is the smallest voltage that can be produced? Okay. So in this case, let's go to the next part. Here we have been asked, of course, we have been asked to work out the resolution also. We'll do that. But first, let us come to this part, resolution of the voltage. So what is the resolution in this case? Resolution voltage, can you tell me? Smallest step that can be produced.
So
5 volts
it would
divided by, and you have 6 bits. So you can go
Yes,
2
sir.
raised to 6.
power 6. Yes, sir.
Okay. So
Yes, sir.
how much is this? It is 5 divided by 64.
64.
Okay.
Yes, sir.
Okay. But suppose if you are to use 2 raised to 5. So your if you use this 2 raised to 64, you will get a value which is less than 100 millivolts, and that is acceptable. Got it? This
Okay.
value will be less than, so this will be less than 100 millivolts. If you are to use 2 raised to 5, what will you get?
5 by
5
32.
divided by 2 raised to 5. How much is that?
5
So
by
0.125.
Yes, so that will exceed 100 millivolts. Okay, so 5
Yes.
divided by 2 raised to 5 is going to exceed 100 millivolts. So does that answer your question now? Why we need 5 bits?
So, but what we have is minimum of 100 now. So if it exceeds, then that's the issue.
It's the smallest voltage. It's the resolution. We can have more number of. We can see what we need to produce, what we need to the smallest voltage that we need to produce should be less than 100 millivolts. It should not be more, but it should be just near to this. Okay, we should not have 2 raised to 7 here. Got it?
Okay, sir.
Because we are talking about the minimum number of bits that are required. If we take 2 raised to 7, then while it serves our purpose, but it exceeds the minimum number of bits that are required.
Yes, sir.
Are you clear about it now?
Yes, sir. Thank you.
Okay. So let's proceed. So I hope this point about producing the smallest voltage, the smallest voltage that can be generated by the DAC is clear to you. In this case, we needed 6 bits to produce this. So if we are to, um, if we are to, let me just, yeah. So if we are to write this, if we are to produce a sketch for this, of course, I will leave that as an exercise for you. Can you tell me how many steps will be there in your ladder, in your digital to analog converter ladder? You see, you have 1, 2, 3, 4 steps here. In the problem which we have taken, in the example which we have taken, you will require 6 steps and you will require 6 bits. Okay? While your VS, that is your voltage range, is 5 volts, 0 to 5 volts. You can go from 0 to 5 volts. So if you apply 5 volts here, you have these 6 switches and you have more number of steps in your ladder. The output that will be produced will go from 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1. Okay. So you are going up to 63 divided by 64 times 5 volts. I hope the point is amply clear now. So you just have to modify this circuit. You have to add 2 more bits to it and you have to extend this ladder a little more. So I'm not doing that part of the problem, that is because it will consume a lot of time. I hope it's clear to you. But of course, the next part also, derive the expression for the voltage output of the above DAC based on the bit status. That means in terms of B0, B1, B2, which are the bits. So in terms of this bit status, B0, B1, B2, B3 and so on, you have to derive this expression. Naturally, you will have to start with the principles of the operational amplifier and then you will have to you will have to come to this second part in which you work out the IN and you say that IN is equal to all this. Of course, there are 2 more bits here. So you have to take those also into account. And here you will get the expression if we are to do it. Now, suppose we ignore this negative sign, then we will have something like this. I'm sorry. Okay. So we will have So we have to work out the expression for. So I'll just erase this, and this part will change the color so that we have to obtain the output, okay, V DAC, V output, and that is going to be, if we ignore the negative sign, then we will have 2 raised to, uh, so here we will have 2 raised to 5 because we have 6 bits. So 2 raised to 5 multiplied by B naught, B5. This is the 5th bit, plus 2 raised to 4 into B4, plus 2 raised to 3 into B3, plus 2 raised to 2 into B2, plus 2 raised to 1 into B1, plus 2 raised to 0. I am writing it as 2 raised to 0, although you know what it is, into B naught. It's just this entire thing here. Sorry. We'll have to reduce it slightly. So this multiplied by Ps divided by 2 raised to 6. Okay. So this is the expression, and you have to derive this expression. That is what has been asked. I am of course not doing that over here. I hope this point is clear to you now. So we have attended to all the points here. So you have to work out the sketch. You have to design and prepare the sketch. You have to derive the expression for the voltage output over here. That has been done, and it has been done in terms of the bit status. So depending upon whether the bits are zeros or ones, okay, you will get different values. And work out the resolution voltage of your design. And we have already worked that out in our previous slide. Remember, we have already it out. So the resolution is 5 divided by 2 raised to 6. So this is our resolution. Okay. This we cannot have because this will exceed 100 millivolts. So this we cannot use. We will have to use this. Okay. I hope everything is clear to you now. Shall we proceed to the next example? We have about 10 minutes. So we'll move to the next example. Yeah. Now here there is, in this example, you have been asked to prepare an offset circuit to scale the output of an 8-bit digital to analog converter, which is in the range of 0 to 5 volts to the range of plus minus 10 volts. Okay. So here our digital to analog converter that we have here, this DAC, it is an 8-bit DAC, 8-bit. This is given to us. And you are required to, the DAC can produce voltage between 0 volts, its range is 0 volts to 5 volts. Okay. 5 volts. Now, you have been asked to convert this voltage from 0 to 5 volts to the range of plus minus 10 volts using an offset circuit. Many times it happens that you want to interface your computer with an actuator, and the drive amplifier for the actuator can take inputs, bipolar inputs. So it can take inputs, maybe for example, between minus 10 volts to plus 10 volts. But your DAC, this DAC can produce voltage only between 0 and 5 volts. So now you have to map the range from 0 to 5 volts to plus minus 10 volts. Okay. Naturally, we are going to use the operational amplifier for this purpose. And so before we work out the details of the operational amplifier, let us formulate the equation for the relationship between the DAC voltage and the output of the offset voltage circuit. So let us work that out. I've got a box prepared here beforehand, and also this icon kept ready here. So first of all, let us say that we are going from 0 volts to 5 volts. So our DAC can take values. So let's say this is VDAC. Okay. And we have to go from 0, we have to produce the range plus minus 10 volts. Now, it has not been told to us specifically that 0 should correspond to plus 10 or minus 10, or 5 volts should correspond to plus 10 or minus 10. So we will take it to our advantage. And because we know that the operational amplifier is going to invert the polarity, so we will say that 0 volts, let it correspond to 10 volts. So here we will take this. Let us say this corresponds to 10 volts. So we have one point here. When you are outputting 0 volts from the DAC, your offset circuit should produce 10 volts. And when you are outputting 5 volts from the DAC, your offset circuit should produce 0 volts. So here you are having 0 volt. So this is the offset voltage, output of the offset. Let us, instead of writing it as V off, let us write this as V naught. Just keep this as V naught. And offset we will use for another voltage that will come, because we have to add a voltage to this. So let us map this. So 0 corresponds to 10 volts and 5 volts DAC corresponds to 0 volts V output. So this is a linear relationship that you have, and you can see that if you, for example, if you have you take this value corresponding to this value of DAC, you will produce an output Okay. So this is coordinate here will be V DAC, and coordinate here will be V output. The coordinate for this point is going to be 5 volts and 0 volts. And coordinate here is going to be 0 volts and 10. So what is the equation of this line? So that is going to be the relationship which we are looking for. So the equation will be like this. V output, so this minus this upon this minus this. So let's say V output minus 0 divided by V DAC minus 5 volts, and this should be equal to 10 minus 0 divided by 0 minus 5. 0 minus. Is it okay? I think I made a mistake here because we require, we have to map it to plus minus 10 volts. So here let us make this as 10 volts. So this one will be minus 10 volts. Okay. I have made a mistake. I'm sorry. So this is going to be minus 10 volts. Minus 10 volts. And here we will have minus 10 volts. So this unit is also going to change. So it's going to be 5 volt and minus 10 volts. So this will be minus 10 volts. And this is okay. Okay. So now it's okay. So here we will have V naught. Here there will be a change. Also here so let us see. So this will be V naught minus of minus 10 volts. Minus 10 volts. Divided by V DAC minus 5 volts, and that is equal to 10 volts minus of minus 10. So V minus 10. Divided by 0 minus 5. So this works out to 20 divided by minus 5. So we have minus 4. And this will be therefore V out plus 10 will be equal to minus 4 into V DAC minus 5. Okay. So this becomes V DAC, so V naught is equal to minus 4 V DAC plus 20, and we'll take this 10 to the other side, so it becomes plus 20 minus 10, that is plus 10. So this in terms of volts, this is our expression that we are going to have. So we will place this in a box. This is what we have to. This is what we have to implement. This expression is what we have to implement. Let us say that we try it out using the operational amplifier circuit. So naturally we can make use of addition. So we have two inputs here. One input is your DAC. Okay. So we can have a circuit like this. We can from the DAC, which will produce a voltage of 0 to 5 volts, we can connect it like this, have a resistance like this, and connect it to the inverting end of the operational amplifier. Because we are going to use a summing configuration. So we have the operational amplifier. This is going to be our output voltage. Let's say this is R1, and this is connected to the inverting end, and at the non-inverting end we are going to ground it because we are using an inverting configuration. And here let us have a feedback resistance. So this is going to be RF. So this will give us minus V naught. V naught is equal to minus RF by R1 into VDAC. So this is our VDAC. But it has to be added. It has to be added. So we need another resistance here. So either we could add it directly, or we could take it through a resistance like this. Let's say this is R2, and here we will take this as V offset. So now we know the expression from our summing amplifier configuration. We know that the output should be equal to minus RF by R1 into VDAC minus RF. If you refer to your notes of a few days ago, you will get this particular summing configuration, the expression for the summing configuration. So here we have R2 into V offset. Okay. So now we can choose the resistances accordingly, R1, R2, and so for example, we can choose you can choose RF. Let's say you choose RF as equal to 1 kilo ohm. You see, this RF value should not be small. It should be more than 1 kilo ohm at least. Okay, And the reason for that is if it is small, then the current will tend to directly pass through this feedback loop, and that is not desirable. So RF is equal to 1 kilo ohm. So here as well as here we have 1 kilo ohm. I'm sorry, instead of 1, let us take it as 4 kilo ohms. Let's make it 4 kilo ohms. So RF is 4 kilo ohms and R1, we'll take R1 as 1 kilo ohm. So we have 1 kilo ohm, 4 kilo ohms here. So this will give us 4 divided by 1. That is minus 4 will come here. And here we will have minus 4 divided by, now we can choose V offset and R2 depending upon the power supply that is available to us. In our case, let us take R2 as equal to 4. If we take it as equal to 4, if you want, you can take it as it's just an example. So you can take this R2 as equal to, so this is 4 divided by, let's say you take this as 2 kilo ohms. Then V offset will actually have to be equal to 5 volts. So V offset we will have to choose V offset as equal to 5 volts. So this will produce this desired effect. So we will have when V offset I'm sorry, when VDAC, so when VDAC is equal to 0, so when VDAC is equal to 0, you will have minus, so be 4 divided by 2, that is 2 multiplied by 5. So here you will have minus 10 volts. So the output will be equal to minus 10. And I'm sorry, you will have to take this as minus 5 volts. You'll have to choose this as minus 5 volts. Then only this will be corresponding to, so VDAC is equal to 0. This will correspond to plus, yeah, so this will now correspond to plus 10 volts. And if you do VDAC equal to, if you try VDAC equal to 5 volts, then output will be equal to what? If you make this as 5 volts, this will be minus 4 divided by 1, minus 20, and here you have plus, this is going to be 4 divided by 2, that is 2 into your offset is minus 5. So minus 2 into minus 5, that is 10. So here you will have minus 10 volts. So you are able to proceed like this. Okay. I hope this example is clear to you.
Yes, sir.
Yeah. So we will. I think we have exceeded our time. And if you have any queries, we will do them preferably in the next class.